Okay. Hello, everyone. Good evening, good afternoon, good morning, wherever you are on this planet. Welcome to our Weizenbaum-Forum on cybersecurity governance challenges in times of growing geopolitical tensions. My name is Volker. I head the research group Digital Economy, Internet Ecosystem, and Internet Policy at the Weizenbaum-Institut, and I have the great pleasure and honor of moderating today's discussion. Thank you all very much for joining us for today's event, and a very special thank you to Cecilia Testart for co-organizing this with me and our stellar group of panelists for being here. Thank you, folks. Now, you may ask, why did we come up with this topic in the first place? So let me walk you through some of these thoughts and give you some context. Our societies and economies have become deeply and in many ways irreversibly dependent on digital technologies, directly and indirectly, with or without awareness. A broadening variety of networkable devices is deployed across homes, workplaces, industrial environments, and almost everyone, right? And everything is always on, interconnected, and computing, and increasingly AI assisted. As these technologies become more pervasively embedded in private and also professional environments, of course, threat landscapes evolve, and cybersecurity risks at the infrastructure, device, product levels are arguably becoming harder to manage. And there are a bunch of, as economists would call, externality, asymmetric information problems at work, which, for example, Anna Maria, who is a panelist today, and I examine in detail in our joint work. So while policies to address cybersecurity and resilience have emerged, we see geopolitical tensions that complicate a harmonized path forward. Now, let me briefly walk you through the landscape. Now, behind platforms, networks, devices, I just mentioned, right, and more broadly behind service provision in today's digital economy, lies a complex and evolving fabric of interconnected and complementary resources. Network computing, from hyperscale data centers to edge locations, communications networks from fiber and 5G to submarine sea cables, software, which includes all kinds of machine learning, AI-related stuff, and data of all kinds. Now, these resources are organized into overlapping multi-layered stacks. Many of you have heard the term AI stack, and also probably how these stacks are controlled by large tech companies. Now, make no mistake, we have witnessed over the last 2 decades or so a seismic shift in the way the internet is interconnected, where servers are positioned, data is stored and processed, and how and from where content and application services are distributed and delivered. Think on-premise, think edge, think cloud, all kinds of stuff. Well, before the recent hype around AI, leading tech firms were building highly scalable, extensible infrastructure substrates that underpin a growing share of economic activity. Now here, again, more recently, AI has driven massive investments in these stacks. And if you include to the picture stuff like softwarization and modularization, we see expanding options for seamlessly combining these resources. Now, the result is that value chains are becoming more fluid, ownership and control structures are changing, and competitive dynamics are being redrawn. Now, here's a critical point for our discussion today. These AI-driven ecosystems are characterized by a fabric, a complex and evolving fabric of technical and business relationships, and a variety of dependencies and interdependencies that are often opaque and poorly understood, even by the stakeholders involved. Now, add to this that the underlying resources are owned and managed by different, very often competing entities with imperfectly aligned incentives and varying capabilities to secure them, report incidents, and collaborate. And you begin to see, I guess, why the security landscape and the cybersecurity threat models are growing ever more complex. Now, the consequences are tangible. You probably have heard of outages at major cloud platforms that have shown how a single point of failure can cascade across entire sectors. So dependencies can give rise to more systemic risks or harm. Now, the deepening interdependencies between compute data and AI model supply chains, for example, now in the case of AI models, combined with growing geopolitical tensions, heightens concerns around cybersecurity, resilience, and digital sovereignty. Now let's shift gears a bit and look at networks. At the network level, Core internet protocols, such as the Border Gateway Protocol, BGP, were not originally designed with security in mind, leaving them susceptible to misconfigurations, deliberate attacks, such as route hijacking. While the resource public key infrastructure, RPKI, for example, offers a cryptographic framework to address some of these vulnerabilities, adoption remains a challenge. I'm sure that we will hear more about this from Cecilia later. Now, this is also, this kind of network vulnerabilities and resilience, if I may add, is also an area where Cecilia and I, along with David Clark and Bill Leary, have explored the internet resilience topic in a joint paper 2 years ago. Now, when we switch focus to the device level and product level, we see an explosive growth of the Internet of Things, the IoT, which has introduced billions of connected products into homes and workplaces, many lacking basic security features. Now, when you think about the security context, traditional perimeter-based security models are increasingly invalid here. A compromised IoT device can act as an internal adversary, enabling lateral movement within a network, replay attacks, long-term surveillance, and so on. Risks especially pronounced in consumer environments without professional security oversight. Now, AI and large language models and so on are now being integrated directly into these devices, while many routinely communicate with servers across multiple jurisdictions in ways often opaque to users and regulators. We have seen that in the EU, the Cyber Resilience Act represents an important policy effort to address some of these issues. And here, of course, I think Anna Maria will talk a bit about this later, and we have also current research collaborations on these topics. Now, having briefly mapped and walked you through this landscape, let me turn to two forces, like cross-cutting forces, that further complicate the picture. I will come back to AI itself. So AI is in a way a double-edged sword. While it can enhance threat detection and cyber defense, it may also be leveraged to launch more sophisticated attacks and identify vulnerabilities at unprecedented speed and scale. AI is also becoming deeply embedded in network operations, from traffic management to automated routing decisions, raising questions of whether this enhances resilience or introduces new risks. As of now, it seems far from clear whether jurisdictions are converging or diverging in how they approach these challenges. Second is geopolitics. I mentioned this before. Coordinated international responses are becoming increasingly difficult precisely when they seem most needed. The EU, for example, finds itself navigating aspirations for strategic autonomy and the realities of a deeply interconnected global digital economy. Questions of how to balance sovereignty, competitiveness, cybersecurity require addressing complex trade-offs. Now, these dynamics and complexities bring us to the questions that will guide our discussion today, and I should note that they run in both directions. On the one hand, where do cybersecurity challenges touch on geopolitical and sovereignty concerns? How is the integration of AI into devices, networks, and critical systems changing the threat landscape? Are we seeing fundamentally new attack surfaces or an amplification of existing problems? And what should governments care most about when it comes to centralized control, dependencies, and systemic risks? On the other hand, where do geopolitical and sovereignty dynamics reshape technical cybersecurity questions? How are governments recalibrating the trade-offs between openness, efficiency, and security? Now, and what are the implications of cross-border data flows and concentrated control over critical infrastructure for the enforceability of regulation? Now, these are huge challenges, and we couldn't be more fortunate, right, to have a truly outstanding and interdisciplinary panel with us today here, bringing together expertise from diverse geographic and institutional contexts. Lastly, but not least, of course, Cecilia Testart. She's an assistant professor at the Georgia Institute of Technology, where her research focuses on internet routing security. Cecilia has done very insightful work on BGP security, RPKI adoption, the stuff I mentioned before, and the institutional landscape of cybersecurity governance. As I noted, we also have jointly worked on questions of internet resilience. She provides a critical technical and US-based perspective on these issues.
Thank you. Well, thank you so much, Alexia and Anna Maria, because especially when Anna Maria finished, like, we need to measure. That's what I do. My bread and butter is to measure the internet, and today I'll be talking about how to measure part of it for security and reliability. And I know that Volker, how can I advance? In his presentation said I come with the US perspective, But the reality is, like, I'm not originally from the US. I was born and raised in South America, in Chile, where I also did a big part of my undergrad. I did also an undergrad in France, and then I moved to the US. And in my research, I have really tried to get the perspective broader than just a single country, because it is, for me, the realities of how, for example, internet works in South America and it works in the US or Europe are so strikingly different that it has always embedded my reasoning. Okay, so I want to start by giving you these screenshots of events, because even though we're talking here about cybersecurity and we know that this is relevant, sometimes we can forget that it kind of happens and how relevant it is. And what I want to, so these are like snapshots from the past 5 years. And what I want you to take out instead of reading this is, like, if you even just skim this with your eyes, you're going to immediately see some names that I'm expecting you're going to recognize. AWS, Cloudflare, Google, Facebook. You also see like Russia, China, state actors. So my goal for this is first to show you that even the largest tech companies that have a lot of funding and that are able and capable to attract the best minds at this moment are vulnerable to attacks because of the network. And there's nothing that anybody that connects can do to prevent some of these attacks, instead of trying to be monitoring them and limiting them. But the moment that one is connected to the internet and there's traffic going and flowing through the internet, all that traffic is vulnerable to this type of attack. Otherwise, we wouldn't see AWS or Google having this type of attacks. The other part is that indeed there are geopolitical perspectives to this, and there are places where there are capabilities that are being developed to misuse certain internet protocols that end up causing this type of issues. So the big first message that I want to pass is that any application that runs on top of the internet is vulnerable. And that applies also to AI, because a lot of the AI flows run on top of these networks that need to connect servers to agents, or that have the data set in one place for training and then the application is another place. So the moment we're extending the footprint of the data flow, we're extending the possibilities of this attack to happen. And I want to explain you a little bit more of how this happens. So I'm going to take like a very well-known hijack that happened in the routing protocol, which is one of the protocols that I work the most on, just to show you a little bit how this is so distributed that it's very hard to figure out and to protect against. So this is a hijack that happened to a cryptocurrency wallet that was hosted in an Amazon cloud service. And what happened, usually for traffic to reach this service that is hosted in the Amazon cloud, Amazon in one of the routing protocols needs to know the world what are the IP addresses to which they respond. Otherwise, there's no possibility for the packets to reach the final destination. What happened that day is that another network that actually, so these servers were hosted in, I think it was US East, so in the east of the US. This network, then it was kind of geolocated towards East Ukraine, so completely another place in the world, started announcing the same set of IP addresses. And by doing so, in a particular way, it started attracting traffic that should have gone to Amazon, but it ended up going to this network. So from Amazon perspective, they're like, oh, suddenly they're not even seeing traffic. So they don't think that they are being attacked in any way. Also, like, this is a service that they're selling, and suddenly there's no traffic. So just to tell you, like, there's absolutely no visibility for Amazon that there is going on. They just suddenly are like not receiving traffic. But then for the users, their traffic was going to a malicious place where there was a fake DNS server that took them to a replica of the wallet. And then instead of doing the transaction to the usual service, they were doing the transaction with the fake infrastructure mounted by the cyber criminals. And that's how the cryptocurrencies were deviated towards where the attackers wanted. And so you can see that here, like, this is a network from Ukraine that is attracting traffic worldwide, and there's nothing that Amazon can do. And actually, like, the harm It's not even Amazon, because this is a service that Amazon is selling, that is the cryptocurrency wallet. But you can even go ahead on that, is that actually even the wallet, they are not the ones, maybe they have a reputation damage, but the people that actually lose the money are the end user that were doing this transaction while this hijack was going on. And currently, the only way that we know how to prevent and limit these vulnerabilities that enable the attackers to do this is that actually not even Amazon, but the networks that connect the internet, all of them need to improve their security practices. So you can see how here is like, there is a whole coordination that needs to happen to start preventing this. Another example that I want to show you, just to insist on like how this can really happen, and this is also because it's a source of inspiration of my research. So these type of attacks are called hijackers. And something that really inspired me is that there is enough documentation to know that there have been networks that have repeatedly done this type of hijack, and they're still connected to the internet. And there was a very notorious case that was called like this infamous serial hijacker that was called BitCanal, a network that initially was in Portugal and connected initially South Portugal, then North Portugal. And now we have reasons to believe that the same type people have moved to East Europe, and that they have set up other networks. So it's like this one got disconnected, but there are the ones that are not disconnected. But for this first network, there was like 4 years of evidence that they had been hijacking different pieces of IP addresses, causing the traffic to be sent to the wrong direction. One of which even included like they hijacked the address space from the government of Texas, and some very well-known cases. But the way that the internet works is for them to really be disconnected is that all the networks that connect to the internet need to agree of not to provide connectivity services. And you can imagine how challenging that is in a global network, where a lot of these hijacks may have impacted the US or some of them South America. And then this network was actually physically located in Europe, and where they are paying for connectivity to a local European transit provider. So you can see the distance between who is there is a business model that requires profit and who is getting the harms of it. So it took 4 years to disconnect the serial hijacker, and it only happened because there are some networks of people, actually through the mailing list of some network operators, is that they decided to manually ban this network. But no other channel or more official channel, you can actually look at the logs. It was the NANOG mailing list that started all of this. Those mailing list logs are published, and that is what got these hijackers out. You can also read there's like some reporting that's being done on this network. So basically the core of this is that the way that our internet runs today, it has 4 key protocols that are at its core, and all of them require some uniqueness to work. We cannot have 2 IP addresses exactly the same in the internet because traffic needs to go to only one place. And that is the same for then blocks of IP addresses. And that is the same when we translate domain names to IP addresses. The idea is that everybody that translates the web page or that domain should have reach the same domain. It cannot be reaching to different completely different infrastructure. The same happens when we start securing this with certificates. There should be an agreement of what certificates are the ones that should be used for providing security. So these 4 distributed systems actually require global coordination because they need to ensure this regards uniqueness. And this is where we extend. This is not purely a problem of one place, but it's really the global internet. And a lot of this currently happens in all of those layers through a technical mechanism that is called the public key infrastructure. And in this public key infrastructure, we need to define something very relevant, which is the root of trust. And all the mechanism, the technical mechanism to provide more security to the internet really depends on setting these roots of trust. So for BGP, for example, these are, and I'll present it later, the research public key infrastructure that has the RIRs. For DNSSEC, it starts with ICANN. For the web PKI, it has certificates authorities. But where we put our trust is really irrelevant for then being able to secure the rest of the internet. And I'll move quickly because this is just more technical of how this mechanism really enables us to assure the records uniqueness, because we can then verify them with one of the keys that is made publicly available. And if the chain of trust is consistent, we can then assure that those are the records that we should be following. And that is for all the different PKIs that are out there securing the internet. And just to show you an example of how this works, I'll use it for the routing mechanism, is that the idea is that the networks now are responsible for issuing the records with the keys that they received, in this case from the regional internet registries, because they are the ones in charge of delegating IP addresses. And once they have those certificates can be validated. So then the networks in the internet, when they see all these different blocks of IP addresses being advertised, oh yes, this network has this block, this network has this other block, instead of just trusting what is in open air protocol in BGP, they can then verify against these cryptographic records that the information is really what was meant to be by the organization that received the address space from the RIRs. So that is how this mechanism, this technical cryptographic mechanism, is then implemented. And this is the example for routing security, but WebPKI also works in a similar way. And for DNSSEC, it follows the delegation of domains. So you can see here how immediately we already have two things. For adopting the security mechanism, there are parts of the internet that need to issue these records and the part of the internet that need to validate these records. And I'm telling you this part issuing the records and the effort for issuing the records and the effort for validating the records, intrinsically, they're not technical. So we already know the mechanism and the techniques, and how to get more adoption in both those sides for all of these technologies is not a technical problem. So, for example, here it's the case for the routing PKI, which is handled by the RIRs. And you can immediately see here that there's already a component that links it to your geography. Because LACNIC, for example, is the RIR for Latin America and the Caribbean. APNIC is for Asia Pacific. RIPE is the one from Europe. AFRINIC is the one for Africa, and ERIN is for North America. So already here, we have a structure that, although works for the global internet, is heavily influenced by what is done in different regions. But by the RIRs that represent different regions. So another thing is that for all of these technologies, there's quite consensus that they are indeed beneficial. And I'm showing you here, again, blog posts or news reports from industry of the benefit for the one of routing. You can also, probably now there's not that many because Google was a big proponent of the WebPKI, and now the adoption is like almost 90%. In traffic. But the same happened when that was adopted. And here you can see various parts of industry. But I also put in here two at the bottom right corner that are from government. Government pushing for the adoption of these technology. And this has had a real impact in those zones to really improve their adoption. So again, here we're saying this is a global technology to secure the global internet, but where a local policy really impacts the changes on how beneficial this can be. And just to also provide you a global view of this, I told you that there are two sides of our PKI. One, the networks and the organization need to issue the certificates. Here is the adoption of those certificates. So again, my idea here, more than you checking which country is doing the best, you can see the variety of colors, which means that we don't have a uniform adoption of this, and that there are definitely regional and local differences in adoption. Now, if we go and look at the other side of it, the validation side, this is also a map that shows you more or less the percentage that is measured of validation for different countries. And you can see, again, myriad of different colors. And that is also, that talks about the difference in regionals and local differences. And just to relate a little bit to the point that Maria told, actually measuring these things is very, very difficult because of the size of the internet. And because we, for example, as researchers, we're third parties. We're not inside the networks that are running this. And even for the networks for themselves, it's challenging to be able to handle all their data to discover where they have points that maybe they have a router that has not adopted. So this is really challenging to be able to measure this. And because it's difficult to measure, it also brings more opaque the benefits of the efforts that we're doing for adoption. So part of it is to improve on this, we really need this collaboration between industry, research, and policymakers so that we can improve how do we see, to really know what is the state of security that is behind our networks, because that also relates to the level of risk that we have. So I told you that all applications that are on top of the internet are vulnerable. So what can we do? Well, we need to adopt security mechanism. However, the security mechanism, they do rely on support and trust. And support and trust are local, and at best, they are regional, which brings us back to how we map this with different geopolitical tensions that may be happening. Thank you.